Hi, welcome to AP Calculus for East Aurora High School. Today we're going to discuss continuity and one-sided limits. In all, what we're going to see is that a graph is going to be continuous at a point x equals c if there are no holes, jumps, or gaps on the graph at x equals c. Let's start by looking at the three ways in which continuity can be destroyed. So the first way in which continuity can be destroyed is if the function is not defined at x equals c. So we're going to draw a picture for each of these. I'm going to go ahead and make my axes here and then draw a graph for which at x equals c I don't have a function value. It's not defined. What that's going to look like, let's say I've got my c value right here. My function might look like this, and then when I get to c, I've got no value, so that's an open circle there, and then it continues on. So what I see is that the function value at c does not exist. I'm going to use the abbreviation DNE for does not exist. So that's the first way that continuity can be destroyed, if I have a hole in the graph or if I have a function value that is not defined at a certain c value. The second way in which continuity can be destroyed is if the limit does not exist at x equals c. So we've talked about several different ways in which limits do not exist. I'm just going to draw one example of that. So I'm going to say, okay, here are my axes. At c, so I'm going to choose a value c here. I'm going to make my function approach c right here and have a filled in circle, and then it's going to continue with an open circle and continue on the way up there. So I see that in this situation the limit as x approaches c of this function does not exist. You'll notice that coming from the left side, I approach one y value. Coming from the right side of c, I approach a different y value. The third problem, the third way that continuity can be destroyed, is if the limit exists at c, but it's not equal to the function value at c. So we'll notice that we have a limit, we have a function value, but they don't match each other. So I've got my c value right here. I've got my function where at c the function value might be someplace up here. So what happens in this situation is that the function value at c does not equal the limit as x approaches c of that function. So you'll notice on the diagram that the limit would approach this point right here, while the function value is way up here, so they don't match each other. And when that happens, I see that I don't have a continuous function at x equals c. So by examining these three ways in which continuity can be destroyed, that's going to lead us to the definition of continuity. So the definition of continuity, specifically continuity at a point. A function is continuous at a point c if the following three conditions are met. So we've got to make sure that none of the problems that we've talked about in the previous page will happen. So the first thing I want to make sure of is that the function value at c must exist. The second thing we want to make sure of is that the limit as x approaches c of the function must exist. So lastly, if the limit as x approaches c of f of x is equal to the function value at c, then that means that I have continuity at the point x equals c. So the examples that we're going to look at today are all going to be based on this continuity at a point definition. First, some notation before we move on. For one-sided limits, you saw this before in pre-calculus. I just want to make sure that you know the notation for us here. If I want to take the limit from the left at x equals c, the notation that we use is the limit as x approaches c, and to denote the left side we put a little negative up above as a superscript on the c. So this means take the limit as x approaches c coming from the left side of the function. For the limit from the right, I'm sure you remember from pre-calculus, this is going to be the limit as x approaches c, and this time we'll put a little superscript of a plus showing that I'm approaching from the right side of c. Let's take a look at this first example. F of x is equal to the square root of x minus 1. So to draw this, first of all, if you need to, go to your graphing calculator, but I'm assuming that you know what a square root function looks like. The x minus 1 should, of course, have shifted this graph 1 to the right. So my graph should look like the upper half of a parabola that opens to the right. Normally it would be touching the x-axis at the origin, but because we've shifted it 1 to the right, I see that it should touch the x-axis at the point 1, 0. So what I notice for this one is that I can take a limit, and the limit that I want to look at is the limit as x approaches 1. But I can't just take the limit as x approaches 1 because I don't have function values on the left side. I only have function values on the right side. So we're going to write this as the limit as x approaches 1 from the right side of the function f of x, which is square root of x minus 1. And I see that that function value should approach 0. You'll notice that, again, I can't approach 1 from the left side because there aren't any function values on the left side. So this would be an important notation for this kind of graph that doesn't exist to the left of 1. The second example, the greatest integer function, we're going to be discussing in class in the next few days. So you can go ahead and skip that one so that we can talk about it together in class. So once again, to review, the existence of a limit is if I've got the limit as x approaches c from the left side of a function equaling the limit as x approaches c from the right side of the function, then what that tells me is that the limit as x approaches c of f of x exists. Again, we can go one step further with continuity then, because we know that if the function value at c exists and the limit as x approaches c of f of x exists, if these two values equal each other, then that means that f of x is continuous at c. So it's kind of a two-step process. We want to make sure that the limit exists by making sure that the left-hand limit and the right-hand limit equal each other. But we also have to make sure that the function value exists and that limit is equal to the function value. If that is all true, then we know that the function is continuous at x equals c. So let's take a look at some examples where we want to use the graph to determine the limit and discuss the continuity. So we're going to look at all three things that we just talked about. If the limit, let's start with this picture, a graph of a parabola. You'll notice that at x equals c, we've got the point noted there. So if I can find the limit, oops, need a pen there, the limit as x approaches 3 from the left side. So if I look carefully at this graph, I see that the limit as x approaches 3 from the left side happens to be a function value of 3. Let's go ahead and do the limit as x approaches 3 from the right side. Notice that coming from the right side, my function value also approaches 3. Because these two equal each other, then that tells me that the limit as x approaches 3 of f of x is also equal to 3. So our 3 parts to our continuity definition. Part number 1, let's look at the function value at 3. Again, at this parabola, I see that the function value at 3 is equal to 3. The second thing, I go ahead and refer to that limit that we just found, the limit as x approaches 3 of f of x. That's also equal to 3. So when that function value is equal to the limit, that tells me that the function is continuous at x equals 3. So that's the step-by-step process that we need to go through to discuss the continuity of the function. Let's try example number 2. Make sure as you're taking notes you are pausing the video, drawing the diagram, and filling in all the information that we know as we take each example. So I'm going to start with the limit as x approaches 0 from the left side. So as I'm approaching 0 from the left side, now I'm looking specifically right here, so I see that coming from the left side, my function seems to be approaching the number 3. So I'm going to say the limit as x approaches 0 from the left is equal to 3. However, as I approach 0 from the right side, I see that that's approaching a function value of 1. So, from the right side, we approach the number 1. Now, because my left-hand limit does not match my right-hand limit, that tells me that the limit as x approaches 0 does not exist. Now, that's going to help us to discuss continuity. So first of all, I want to say, does my function exist at 0? If I look closely, it looks like 2 empty circles at 0. So that means that the function value at 0 doesn't exist. As soon as one of these things does not exist, I know that the function can't be continuous. I'm going to write down the other thing that does not exist as well here, though. The limit as x approaches 0 of the function from above, we know that that does not exist. So since both the limit don't exist and the function value doesn't exist, that tells me that f of x is not continuous at x equals 0. We're going to see in tomorrow's lesson that we call this a discontinuous function, and we're going to see all the different types of discontinuities that a graph can possibly have. Example number 3 looks like the following. So again, take a minute to draw this graph in your notes and write down the information that we're going to be finding. We see that we've got the limit as x approaches -2 from the left side. So as I'm approaching -2 from the left side, it's along this branch right here. And let's see, I think that looks like a function, a limit, of 5. So I'm going to say as I approach from the left side, I'm getting an answer of 5. Now, as I approach -2 from the right side, I see that that's giving me a limit of 4. So since the limit from the left does not match the limit from the right, that means that the limit as x approaches -2 does not exist. So when I am discussing continuity, let's see here. Number 1, I see that there is a function value at -2. I'm going to find that function value where the graph has a filled-in circle. So the function value at -2 is equal to 5. However, where I ran into trouble with my definition of continuity is that the limit as x approaches negative 2 of the function f of x does not exist. So I can't possibly have a function value equaling a limit that doesn't exist. So that then tells me that this function f of x is not continuous at x equals negative 2. Now this whole process may seem a little tedious, but I promise you, you're going to have some multiple choice questions, whether it be on a test or midterm or possibly the AP exam, where you're going to have to examine all the parts of the continuity definition. So that's why it's really important to know which aspect of the continuity definition is failing and giving us a function that's not continuous. Let's go ahead with this last example. You'll notice that it's set up a little bit differently, but we're going to be looking for the same information. I've given you the graph of this, but notice that we haven't really zoomed in on this graph, and it might be helpful to look at this graph on our graphing calculator as well. It's the rational function, meaning a fraction function. F of x is equal to x plus 2 over x squared minus 4. The first question says, where is this function discontinuous? So the first thing that we want to take a look at is our denominator. So we're going to take the denominator x squared minus 4 and set that equal to 0. When we factor this into x plus 2 times x minus 2 and set those factors equal to 0, we have two places where the denominator turns out to be 0. X equals negative 2 and x equals positive 2. So the two places where my function is discontinuous is going to be x equals plus or minus 2. So then the question says, well, let's talk about the graph at each of these discontinuities. At negative 2, it's very difficult to see what's going on here, and again, in the next few lessons, we're going to be taking a look at types of discontinuities. You might remember from pre-calculus that when I have a numerator and a denominator that are both equal to 0 at a particular spot, so for example at negative 2, the numerator is 0 and the denominator is 0, giving us an indeterminate form. What ends up happening in that situation is that at x equals negative 2, I've got a hole in my graph. It's easy to see the other spot at x equals positive 2. I see that I have a vertical asymptote. So at each of the discontinuities, I've got two different situations. I've got a hole in the graph at negative 2, and I've got a vertical asymptote at positive 2. Now let's just discuss the left-hand and right-hand limits at each of those spots. I'm going to kind of draw a line down the middle here and go ahead and look at each of them. So at x equals negative 2, let's do the limit as x approaches negative 2 from the left of this function. Now, as I'm approaching negative 2 from the left, it may be a little bit difficult to see what this function is actually approaching. But I do see that the limit as x approaches negative 2 from the left is going to be the same as the limit as x approaches negative 2 from the right. Again, in our next few lessons, we're going to see how to calculate what that limit is. So for today, I just want to take a look at this and say, oh, those two limits do match. So what that tells me is that the limit as x approaches negative 2 of this function does exist. Our problem, though, for continuity is that there's no function value at negative 2. So therefore, the graph is not continuous at x equals negative 2. At x equals positive 2, we've got a completely different situation. We see that when we take the limit as x approaches positive 2 from the left of this function, and again, look carefully, as I'm approaching 2 from the left, I see that my graph is going to negative infinity. So I'm going to say negative infinity. As I approach 2 from the right side of this function, And again, I'm looking at that vertical asymptote at x equals 2. Approaching that, I see that my function approaches positive infinity. So because one side is approaching negative infinity and the other is approaching positive infinity, that tells me that the limit as x approaches 2 of the function does not exist. Now, as soon as I get a limit that doesn't exist, I also know that the function value does not exist. So again, that tells me that this function is not continuous at x equals 2. So we've taken a look at the idea of continuity through all of these examples. We're going to continue with this in class and then proceed on to discontinuities over the next few days. If you have any questions, please come and see me. You can rewatch the video at any point and make sure that your notes are complete for this lesson. Thanks. Have a great night.